Yeah, recording started.
All right. Yeah, so hi everyone. Welcome to this week's Saturday afternoon session. So today we're gonna look at a category of problems that are basically like designing data structures where you're given like a class or some sort of a data structure to implement, and then you have to fill in the methods of that class. So I've posted the handout link. Let me post that in the chat now, and then I'll also share my screen. Okay, is my screen visible?
Yeah.
Okay. Yeah, so the first problem will just be to implement a trie or prefix tree. So maybe like we'll just discuss like what a prefix tree or trie is first. So does anyone want to like say what is a trie? Anyone familiar with a trie data structure?
In array with characters. Basically, each node represents a character, and then like you'll have multiple hierarchies like leading up to the word or sentence, whichever we want to store.
Right.
They're efficient for lookups, like
Right.
fixed-based lookups.
Yes. So a trie is one of those data structures. I covered strings the last two times I led the session, and I was wanting to include tries as well, but I never really got a chance. So as Naga was saying, tries are useful for looking up prefixes of a group of strings. So let's say if you have some group of strings like S1, S2, S3, etc. And then you have some prefix P. So, and you want to know quickly out of all of the strings in this list, which ones start with the prefix P. A trie is a really useful, or like probably the best data structure to use for that kind of problem. And as far as like other real world applications, does anyone know like when tries are typically used?
Can it be in dictionary?
The auto-populate?
Yes.
Yes, so auto-populate or auto-complete.
Autocomplete, it's called as, yeah.
Right, exactly. So like this will be like, let's say you're typing in some query like whatever, the sky is blue or something, and then if you do this on like most search engines, you'll get suggestions, and a lot of times that is implemented with a trie in the back end. And there's a few other use cases, but generally, like basically anytime you have a group of a bunch of strings and you want to quickly check if like which strings in that group match some prefix, a trie is like a really useful data structure. Okay, so In this example, we have to implement the insert, search, and start with methods. So insert is just like straightforward inserting a string into the try, and then search basically will return true or false depending on if that entire string is contained inside the try, and then starts with will return true or false depending on if just that prefix is contained in the try. So if you see this example, first they insert apple, and so searching for apple returns true because apple is in the try. Searching for app returns false because even though app is in the try, app is not a terminal node. So that returns false, but starts with app will return true because that's the difference between search and starts with. Start with doesn't have to be a terminal prefix. And then when we insert app, then search should also return true. All right. So does anyone have any ideas how we would go about implementing a try?
Two approaches, like we can either use hash maps or arrays.
Yeah.
Like
Right.
and similar to like list nodes that we or tree nodes that we have.
Yeah, exactly.
Mm.
Do you want to give that a shot, Naga, to implement?
I have done this many times, but like I'll give someone else an opportunity.
Okay. Anyone else? Seems like people are kind of tired today.
But yeah, I haven't done try before, so
Yeah, you can give it a shot, Naga.
no, I haven't done it before, so I don't know. That's what.
No, you can try. I mean, like now that you understand the concept, you can
Mhm.
give it a try, right? Like the main idea is like you know how the tree nodes and how you have structured like the binary trees, right? But
Mhm.
instead of just having two children, you'll have possibility if you assume like all lowercase letters as in the question, you have 26 children, so you can have an array of the nodes which are of size of 26. So as long as, and to probably index, you can use the whatever the character minus whatever the smallest one.
Yeah. Yeah, and maybe before we jump to the implementation, I guess we can just kind of sketch
Yeah,
that out a
just
little bit more.
yeah. If you sketch some example, the same apple or apple, I think
Yeah,
that will
so
be
let's
clear
say
for you too.
we do try
Do you
that
want to
safe.
use a diagram like to represent this
Yeah,
like the
that's
tree structure that will
a good
easily
idea,
understand?
actually. Yeah.
Typing might not make it clear, so
Okay, let me switch to the yes, the whiteboard. Okay. So as he was saying, it's a tree structure, and every level of the tree represents like the set of characters up to that point in your string. So if your string is apple, you would have a root node which contains an A, and then like let's say this is the root node. It can have other.
yeah, root node is normally empty, so you can just assume,
Yeah.
Mm-hmm.
So it'll have A, and then at the second level, there will be a P,
Mhm.
and then followed by another P, L, and then E, and then you would need some sort of a marker.
Say this is a word. Yeah.
Yeah, to say that like this this is like a terminating node, meaning that everything leading up to this is like a full word. So that was basically like, if you remember the search and start with, search will only be true if the ending node is a terminal node, but starts with, like if you just search for app or you do try dot starts with app, this doesn't need to be a terminal node. And then let's just, to make this like maybe a more complete example, let's say if you added another word like bat or something, then this would also have a B. A and T.
So what would this look like if you had already added in app as well as apple?
Yeah, so if you add
Then-
app as well as apple, then you can keep, you wouldn't like reinsert the same letters, so you would traverse down to here and then you'd say, okay, you'd mark this as a terminal node.
Even though it has more after.
Yeah. So
you
it can,
basically just have a marker saying it is a word, but like you
Yeah.
can continue looking for other words.
right. And so, and also as Naga was saying that, so this tree can have up to 26 children, like every node can have up to 26 children, depending on what you insert. So your node class would either be like an array of 26, like size 26, or a hash map, depending on like which way you want to implement it.
Yeah, that makes sense.
Yeah. So Naga, do you want to give it a shot?
Sure, let's see. I haven't done that, but let's try it out. Do you want to?
Yeah, I stopped sharing my screen. You can share yours if you want to do it that way.
Where do you want to do it? Let's see. I'll use
If you-
it could editor itself.
Yeah, if you want, you can pull up the lead code question.
Oh, is there a lead code on it?
Yes. And then you can like, it'll have the skeleton of the class, and then you just have to fill out the methods.
Oh, let me do that actually. So share my screen.
Yeah, I just posted the link.
Oh, you got the link. What is the number?
It is 208.
Wait. Okay. So let's do the tree itself. We have the class tree.
You're using C++?
Yeah.
Okay.
Okay. So we do that insert, right? Insert, and then I don't know where to start. Sorry.
Yeah,
So
well,
define the node first, probably. And node structure.
Right.
Mm.
So
Outside.
and all three of your methods, insert, search, and start with, will be pretty similar. Like basically for every one, you're just traversing down to like some level of the try, and then like for insert, you're just inserting nodes if they're not already there. And then
Okay.
you mark the last one as terminal.
Mm-hmm.
And then search and starts with are almost identical. You just traverse down the try as long as you have nodes that exist. And for search, if that final node is a terminal node, you return true. Otherwise, you return false.
So instead of directly putting, like you might want to put this in a try node in its own class so that you can.
Yeah, that's up to you. You can do it
Yeah,
either way. Yeah.
either. Okay.
So what was your suggestion? I was thinking like node is a character, right? So I just made like a character and the link, and that node could be a terminal or not. And I'll have a try star. I don't know how many. It could be anything, right? So next, something like that.
So almost, but I would say your list should be a list of try nodes if you do it this way, or like a list of try star.
Okay, so everything I'm making it okay. List or try star.
Yeah, yeah.
Yeah, and then I'll have a have as the data, right? I'm thinking like
What is the next in this case? Like if you already have a try as
Yeah,
children, you can remove the next, I think.
Yep.
So, and you can rename the node as children for better understanding.
checks, making it easy. Okay, so now we made it like the try is like we can continue to have as many try nodes as possible.
Yeah, and just one other thing. So list in C++, is that like just basically like an array list?
Yeah, it's like an array list.
Okay.
That will be
Just
the
for like quick lookups, I would suggest either using a hash map or an array of 26 letters to hold childs.
hash map of the character and the next
character to try node basically, or character to try.
Yeah, your lookup should be constant time. So if you use array list, you'll have to loop and find which character, right? So yeah, I think that is fine.
Yeah, and then you don't need the car data on line 8.
Okay, so now it has the data and the next node. Okay, it's like complete try. I was trying to make a node, but node is the map. Each node is the map in the try. Right?
Yes, yeah, you could think of it as like the subtrees of the try are themselves also tries, and then that way you don't need a try node class.
Okay, so that's good, right? Hanif, maybe you should try it. I might take a lot of time to do this.
Okay, so
sorry.
Well, can I give it a try?
What does the root of the whole thing look like? Just
the
like
root. So like when you initially call the constructor, like on some, like when you just call this constructor, like that will be like your root.
So in this case, you
need to have your root object instantiated. So every time you do insert, you need to insert the word try. Yeah, the other two are like utilizing the try and finding whether you have the nodes or not.
What is taking here when I do the new here?
Yeah, and that's why I mean, like I was thinking like if you could initialize a node outside of the constructor, so in that case you can just initialize the root node. But anyway, like
I think that part is fine. Yeah, so all three of these methods you're going to be looping through the input word or prefix, and basically
Okay.
have a loop through that input word.
Mm-hmm.
And then you check if the map contains and before the loop have like a try node like current or something.
Mm-hmm. Just how would I get the current here?
Yes, and so I think at least in Java you could say current equals this. Can you do that in C++? Like to refer to this class or like this instance?
This dot. Oh, so you want in this function?
At least
I don't think so. There is a this in this. There is a this in C++ also. But I didn't get what you were trying to.
Yeah, well, at least in Java you could just say current equals this.
That's right. Mm-hmm.
Yeah, which would mean it's like the instance of this class. So that's like your starting point or your root. And then inside the loop here, basically you check if current dot it would be child's, I guess, contains
current.
Yeah.
It's a map. Then we are checking if
it has the current letter, which would be I.
Is if it contains this one.
Okay. So if it does, then you basically just update your current pointer by saying that current equals child.get I, or however you index the hash map in C++.
Yeah. Now I don't have the index.
Well, like just look up I in child's.
Okay. Okay. I think Santosh, you want to try it out? Okay. I think I'm lost in this.
Yeah, I can try.
Okay. Take over right then.
But I will just do it my way. I won't use the map. I will just use an array. Is that fine, Hanif?
Yeah, that's fine too. Yeah.
Okay. Can you just allow me to share?
Yes, I guess.
Is my screen visible?
Yep.
Okay. So just this one will be to write all the prefixes. And then I will have one more private function to initialize the nodes. It's initially okay. So less than 26. Okay, so here, okay, I need to actually initialize something like root. And then root. Okay. Okay, so insert. So node start, I'll say crawl is equal to root. Right, and then
Could you give us an idea of what you're
well,
doing
okay.
at the time?
Yeah, actually I just
logical.
created this structure try node. So this will have my pointer to all the 26 children, and this will be the terminal notification, like, you know, so saying this is a terminal node, and this will be the value which I'll be updating all the prefixes. And this is just a function, a private function, which I'm initializing any try node to its initial values. So what I'm trying to do is I'm initializing all these childrens to null, and then I'm actually assigning this leave variable to be false initially, because we just want to set this to true only when the word is, we are at the end of the word, right?
So what is the string here? The string val here, Santosh?
So this will be our prefixes. So I'll keep on updating the prefix for each and every. So it will be easy for me to find when I run through the starts with. So I'll just keep on looking for this value.
Okay.
Yeah. So in this, so this will be word size, and then I'll just run for this one. Okay, let me first write the prefix string also. And then I plus plus. So I'm going through each and every character of the word. Okay, and then I'm just populating my prefix string also. So this will be word of I. And I will take an index, you know, to find out the index of each and every character. So this will be just a. So I'm just trying to find the index of the character, you know, so I can map that with the children. And then if my crawl dash children idx, okay, is null. So then what I will do is I will actually return. Oh, sorry. No.
Yeah, it's insert. Yeah, so in this case, you'd have to.
I have to insert,
create it. Yeah.
Crawl, 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 and idx will be get try over, right? Yeah.
So on line 31, should that be prefix equals word?
Oh, sorry.
Yeah.
It's equal.
Yeah.
Plus equal.
Yeah, yeah.
So this is one, and then crawl, because I'll have to move to the next node, right? So I'll have to actually, right? Yeah. So whenever I'm done with inserting one character, I'll have to move to the next one, right? So again, I'll go in this for loop and I find if for the next character, I'll again create its index and keep on moving down the tree. Okay, but in case if I am at the very end, okay, when I is equal to n minus 1, I will just set my this okay. So here I'm actually setting this leaf variable to true, so it will be a complete word.
Can you
right?
Get try node, Santosh? What was done to?
Yeah, so the get try node actually it doesn't do much. Actually, it just creates a try node and initializes all its variable. So what it does is sets the leaf to false and all of the children's to null.
Oh, so everywhere, every node is like a full try node.
Right.
Oh.
Yeah. Because it becomes easier when we actually try to, insert more number of words. You will just here, if you see, we're just going checking for if it is null. So if it is null only, then I'm going to create it. If it's not null, I'll just go and keep on updating it, right? So wherever I need, I'll just update that.
Yeah. Just one small thing, Santosh. So you can, let's see, what line is that? 36. So you can actually do that outside the for loop, because like at the end of that loop, since crawl is defined outside the loop, it'll be the last.
But in your diagram, you mentioned, like at the last word, the last letter of the word will be a terminal node, right? So that is what you showed in the diagram.
Yeah. So that's what I'm saying. So you should be able to do that outside of the for loop. I mean, it's not a big deal, but.
Okay, then I'll have to.
Yeah, and you don't have to have the if statement.
Okay.
No, you can, because you won't need I.
On line 37 won't be needed.
Or you say just.
Yeah, you could just get rid of that line.
But if I do it on the last one, it will be to the next node, right? If I come out of the for loop, will it not?
I don't think so. I did it with like a for each
because
loop.
that was my thought, so therefore I actually did it inside.
Well, I think it's not going to the next one, right? Because after that, then you go into the for loop, the condition is for, so it, just for out.
Okay.
So the crawl still remain the same.
Yep.
One more thing, like what you're gonna do with the prefix?
So the prefix actually, when you do go for that search, what do you say, starts with, right? So it is easier for you to look for those.
Yeah, but right now you do insert, right? When you create a prefix variable, and what you're gonna do with it, because there's a local variable, then when you get out of it, and that's
it should be. I believe it should be crawl.prefix.
Oh yeah. Sorry.
Yeah.
Yeah, you're right. Yeah.
On line 31.
Okay. I actually have to move it up, right? That is what you're saying, right? Okay. So no, this should be also fine, right? So you can actually add it over here.
31 wouldn't. So go back to your go up higher to show us what you put in the struct. Yeah. So that, okay, the value there. You said that's the prefix. That's everything that appeared before.
Yeah. So see, this is the val, right? Actually, I'm. So this val actually.
No.
So Santosh, I think on line 31 you could just do crawl.prefix. So because prefix is, or sorry, crawl.val.
Yeah. So I did it over here. So you want me to do it on line 32 or 31?
Yeah, I guess that
also should be fine, right? Yeah. Like this, right?
Plus equals word.
No, I think I'll keep it here like this. So does that make any difference if I keep it here or here? Because I'm just actually...
Yes, it makes a difference because you're advancing crawl on line 35.
Okay. So here, this should be fine?
I think that should be fine, yes.
You even need a prefix local variable, right? If that's the case.
Yeah, you don't really need the local. You don't need prefix, I think. But it's not, yeah.
Yeah, but then how I'm going to go it for the next one? Because, I need a cumulative one, right?
No, it's actually not cumulative. It's only the current letter.
No, I'm not doing it like that way. I'm just saying if it is A, first it will be A, then second will be AP, then third will be APP, and then APPL, and then APPLE. Okay, let us move ahead and then we can come back on this. Okay, let us finish the others.
Yeah, sounds good.
Okay. Yeah. So for this, I'll just copy most of the code from the top. Okay. I don't know this one. Okay. Anyway, I'll just copy everything and then modify. So here, this will be the same, this will be the same, and I would say here, okay. I'll just add one condition. If n is less than or equal to 0, to return false because I have not found this word. That is okay, no problem. So this should be fine. Okay, I don't need this here. I'm just getting this guy, and I will return here, right? Return false, right? If I don't find it, yeah, and then I'll just keep on crawling, or at the end, so I will have to return crawl dash val equals 1. Okay, and crawl dash leaf equals true. So I doubt, because I will return it. Okay, let me check that later. Okay, is this okay, Hanif? What I'm trying to say here is, I just go down all the tree, and then I exit this for loop. I try to check this val, which was the prefix which I was actually populating earlier. Compare with the word. If they are same and the crawl leaf is true, then I will return true.
Yeah, it generally makes sense. The only thing I did different is or that I'm not sure about is why are you storing it cumulatively? Because that's extra space, right? And you already have, you can already get the state.
So what I was doing, if I go for starts with, that might be helpful, because I just have to compare it over that.
But for
be more sure.
Starts with will basically be the exact same thing as search without that last condition.
I can remove that if you want to. So I'll just remove that.
I'm a little lost why.
We don't need that prefix at all, or the keeping the value with the node. We don't need that.
Okay, no problem. I'll leave it. Okay, so I'll remove that later for the above. Is it fine? Okay, and then I'll go for this guy now. Starts with. I'll use the same stuff, because it might be more similar to this one, right?
Yeah, it should basically be identical, except for that last condition.
Yeah.
You could just return true right here.
So if I say this is root, and this is not the word, right? This prefix here. Prefix, right? And then okay, let me keep this. No, this should not be here. Okay.
It might be easier if you just change the argument name to word. That way you don't have to change all your code.
Does that work?
Yeah, that's fine. Yeah.
Okay, so I come here and then, okay, I don't need this prefix here, right? So IDX will be there. I go through this children, I look for null, return false, or I just keep on going down. And then if this won't be there, this condition won't be there, right? So
right. So if
just I return true.
Return true.
Yep.
If you get to this line, then you're already good.
Right. Okay, let me remove all the prefixes then. This one also, right? Okay.
You would need that.
Actually, there's something that doesn't work. Where's see the first function that you wrote?
Which one?
The first function below. So
insert?
I think, yeah, I think so. If you go down a little, sorry, maybe it's on. No, maybe it's on search.
Okay.
Oh gosh. Okay, actually it's higher. I'm sorry.
Yeah, it's like okay. Let me see if I'll just remove this also, the string. I'm trying to remove the prefix, which everyone thinks it's redundant. So let me remove. I'll just try to compile, then I'll see if there are any errors. I'll just, oh man. Okay. Will this go away?
Might.
Wow. Good. That's that. Oh yeah, it got compiled, right? Yeah. So actually, yeah. So the prefix is removed, right? So what I'm trying to do in the insert, just going through that and then getting the index, and for the search, right? Okay. And this starts with, right? Maybe it's not very optimized, but on a high level, I think, because I could have used, instead of a vector, I could have used a map, right? The way you were saying, unordered map.
Yeah.
Yeah.
Someone
But
was
I think I remember this most of the time, therefore I
Yeah, I feel like there's a lot of duplicate code with between the search and start with.
Yeah, so I could make a separate function out of that, right? And then use that function over here, correct? Which will be common. I can remove all the common functionalities and put it in the function.
Yeah, I think so.
Yeah.
So the last line is the only one that,
Yeah, so I could actually call that also, search. Yeah. Okay.
For now, it's okay.
That's fine. Yeah. Okay. I'll just try to see submit and then. Yeah. Okay.
Yeah, cool. Sorry, I was replying to someone in the chat. Yeah,
Okay.
that's basically that's pretty much exactly what I did as well, except I used a hash map.
Yeah.
And as somebody was saying, like, yeah, all three of these methods are very similar. And basically what you're doing in every one is just like traversing through the try with all the letters in your word. And for insert, like if the word is not there, so basically the only thing that kind of changes between insert and search and starts with is what you do when like in that if statement when the current letter is not there.
Yeah.
And then the only difference between insert and search is just that very last line, depending on whether that node is a leaf node. So of course you could, like somebody was saying, you could generalize this to like one method and just
So,
but yeah, this is the general idea. And
so we are not storing the character value for each node. I mean, I know
so
that
the character value will be inside that array, whatever it's called. What is it?
The children.
Yeah.
no, but this is okay. Maybe I missed.
So actually what we do is we go through the index,
Yeah, exactly.
Yeah.
I mean, we are going through the index here. So, but we don't have a actual value stored because the index gives us.
Right. Exactly. Yeah.
But if the question like changes, like instead of 26 character, we have like 56, like capital A and small. Right now we are assuming that it's all small letters, right?
Yeah.
I mean,
so the best way would be to use an unordered map, and then you can have a mapping between a character, and then a try node,
Exactly. Yeah.
So that would be the most efficient way of doing it, and a more generic way also.
Yeah. And another thing to note here, especially in terms of thinking about time complexity. So if you look at all three of these methods again, the only parameter that you have as an input is the prefix, like the word parameter. So so I guess I'll phrase it as a question. Like, what would the time complexity be of all three of these?
So I think it's going to be, for the time complexity, it will be the word length.
Yeah, exactly. So in other words, it doesn't matter how many other words are inside the try. Like you could have maybe like there, it's pretty common for certain things like autocomplete to have a try that contains like every English letter in it, for example. So it could be like 500,000 different words, and the complexity is still only like, it doesn't change the complexity at all. Of course, it'll take more memory, but as far as the time complexity, it still only depends on the length of the input prefix.
Right. I got what you're saying. Yeah, that makes sense.
I think in this approach, in terms of space complexity, so for every node, we are creating like 26 nodes and pointers here, right?
Yeah, so we have an array of pointers. Yeah.
Yeah, and I mean, like whenever we have to create a node, whenever we have to add a new character, like every character in the word, we are creating like 26 pointers.
Yeah, but they are just array of pointers.
Yeah. I mean, isn't there like a dynamic way to create something like that? Do we really have to create 26 always?
So you can use a map, right? So another map should be the best way to do. So
Yeah.
you'll only create a node whenever you require it. So you don't have to have this fixed size always.
So Hanif, is your approach using the map way, or like it's also creating?
Yeah, I used the map, and the code is pretty much identical. Like the only thing that changes is how you index the map versus the array. But yeah.
Yeah. Okay. Sure.
I have a question. Let's say suppose they ask like, give me all the words that have this prefix, and what we need to modify to achieve that. So for example, in this the app, right? And we say, okay, they ask like, return me a list of words that have this prefix.
Right. So in that case,
because we have
basically you'd want all of the child nodes of that prefix, and you could modify it, like you could add another method that basically like it traverses down to that prefix, and then from that prefix it'll go to all of its children that are terminal, and then like add those to like a list or something, and that's how you would solve it.
So maybe are you trying to say that I can have something like here as a list of strings? And then
There's some interference.
can someone actually
on mute? Yeah, thanks.
Okay, so it's like, can I have something here like a vector of string, something like that? Will that work?
Yeah, you don't need that, I think, because we already have the information, right? We just like go all the way to find the word and then add it to the result.
You could, yes.
But I think like if you're using for some real time, maybe it's better to cache it at a node. I mean, it depends on.
Right. Yeah. Okay. Cool. Just in the interest of time, I want to move to the next one.
No problem.
But thank you. Santosh, that was good.
Just one clarification on the code. So we are doing -a, right? And it's a small a. If you want to be safe, if you can do always, let's say, first printable character, because if the letter start with capital letter, this will go in negative index. Okay. So just, I think in this the test cases are okay. But whenever we are doing this, either we do with the capital letter, or maybe the first printable character, that is I think space 31 or 32. That would be the safest way to do it.
Harris, for this implementation, he assumed that there will be only 26 alphabet.
Okay.
So I'll have to change it everywhere.
In fact, the test case also passed, right? So I'm saying that it is fine. But just to make a note, I agree. I mean, in fact,
but if you do with the capital A, then how would you find the index?
Basically, you would have done 256, and everything works. You can basically blindly go with 256 and, start
Oh,
with
okay.
the zero.
Got
Yeah, so something like that. I mean,
Right.
just a way to figure out it. Perfectly fine in this question because test also passed.
Yeah.
But just to keep in mind.
Sure. No problem. Yeah. Thank you, Bhavesh. Yeah.
Thank you. That was a good discussion. Let's
Thank you.
move it to the second question. All right, so this one's a little bit longer, so maybe I'll give everyone like a minute or two to like read the full problem. Okay. So this is kind of an interesting problem. Basically, you have to implement an in-memory file system and implement a few of these like common Linux commands like ls, mkdir, and reading from a file and appending or adding contents to a file. So probably in the interest of time, like unless somebody really wants to take a shot at this one, I'll share my code once we get to that point. But let's have a discussion about it first. So does anyone, like what comes to mind in this problem? Like how would you go about solving this kind of a problem?
I mean, since we did a try problem earlier, I mean, obviously, like first thing in my mind, like, can we just use a try, you know, similar to try?
Yes.
So we may like, you know, need some additional properties or data structures. Like maybe like we are storing children. Children can be directories, and also we may need like kind of a list of files maybe under each at each directory.
Right.
And string value to store the content.
Yeah, so that was, the ordering of these two problems was somewhat deliberate because you can solve this with a try. And if you look at the discussions in the LeetCode link here, like for this problem, that is how, like a pretty common way that people solve this problem. I'm kind of undecided. Well, so I'll put it this way. Like when I first solved this problem, I didn't solve it with the try, and that didn't really come to mind. I just kind of made like the directory tree structure with files and with subdirectories, and I solved it that way. And as far as using the try, I'm not sure if it's one of those cases where like it happens to work for all four of these methods that you have to implement. But just from strictly like speaking from a design perspective, like if you were actually designing a file system, I don't think most file systems are actually implemented with a try. But it is an interesting approach.
So, otherwise, without a try, you just have a two lists with one list carrying all the directories in the order, and the second list having files in the respective indexes, file names in the respective
Yeah, exactly. Or better than two lists, two hash maps works really well. Like where you can map so that you have one for files at a given level. And so you would map the file name to the file contents, since in this case, both of those will just be strings. And then for directories, again, you could list like that directories, the subdirectory name to like your subdirectory object. So you get like nesting.
Yeah, a directory can contain multiple directories. Is that right?
Right. So directories, they have like a tree-like structure, of course. Like you can have arbitrarily deep nesting of directories.
Yeah, I remember, in one of the design pattern that have a composite pattern, which is, probably match with this case, because, a composite can be a directory or a file, and a directory can contain multiple directory.
Interesting.
Yeah, yes, this actually fits that pattern.
Okay, cool. Yeah, if anyone wants to like write that solution and share it with the group, that would be, I think that would probably benefit everyone.
So one thing, Hanif, you said the content will be string?
Yeah, in this case, so if you look at the example that they gave, like, so these are the input here, they're like two parallel arrays where the first one is the operation and then the second one will be the parameters for that operation. So for add content to file, they're saying that the file name is, it's ABCD, meaning that it's in directory ABC and then the file name is D, and then the file contents is hello.
Oh.
So both of them will be given as a string in this case. Like you don't have to worry about file encoding or anything like that.
Yeah, makes sense.
Yeah. Any other questions or like thoughts about this one? You have to read some of the things carefully here. Let's like, for example, okay, given.
Yeah, that is what I was thinking. Like, what are the corner cases? One question is the big, but what are the corner cases of where we can go wrong?
Right. So one thing is like for ls, which lists all the files and directories in the current path, or the path that you pass. The output should be in lexicographical order. Another thing, what was I thinking of? Okay, so yeah, for makedir, you create the directory, of course. And then if the middle directories and the path don't exist either, you should create them as well. And then also for add content to file, if the file doesn't exist, you have to create the file with that content. If it already exists, you append to the file.
Yeah, I think these points which you are reading, it kind of give a clue as what Santosh was explaining about the try, the implementation. If
Yeah.
it exists, then you don't do anything, and if it doesn't, then you create the node, kind of idea.
Right.
No, I mean, even with the solution that we have been discussing of using maps, right? Even with that, you could implement all these things, right? I mean, like you don't have to have the try thing.
Yeah. I think, yeah, you could do it either way, right?
Okay. Yeah, I think I missed that part, but yeah, I joined late. So.
Yeah. One question on what Leon was.
Lexicographical order.
Yeah, lexicographical order just means like alphabetical order, like sorted order for strings.
But do we store in that way, or like do we? I mean, sort it. Like, I'm just thinking.
While displaying, I think.
I didn't store it that way, so I just call sort on like before I return.
Okay.
But yeah, there might be a way of storing it to like avoid having to sort. Did somebody else also have a question?
Yeah, one something that Leon was suggesting, I didn't quite follow that. I think was his suggestion like if you have directories inside the directories, the approach wouldn't work, or what was the suggestion there? Or just to use the pattern?
Yeah, I just recall, there's a composite design pattern, and it match this case, because if you look at the node can be either a directory or a file, right? So under, if it is a file, then it contain the string, the content. And if it is a directory, then, it can contain a list of file or a list of directory.
Okay. So the pattern fits well here. Okay, cool. Thank you.
Yeah. That's good to know.
Yeah.
So unless anyone has any last questions, like we can just jump to the code, I guess.
Yeah, please. Yeah.
All right. Maybe I'll try showing it in my IDE just because I like the syntax highlighting better. Let's see, where is it? Yeah, and let me see if I can make this bigger. I guess not.
Yeah.
So is this visible, or if not, we could switch to the browser because that has a zoom function.
We are not able to see your IDE yet.
Oh, I'm not even. Am I sharing your screen? Am I sharing my screen?
Sharing only the browser. So.
Oh. Okay, it's not a big deal. I think I'll just stick to the browser then. Yeah. Okay, so let me minimize this. So yeah, I solved this for the first time like a couple of days ago, and it was like my first time solving it. So there might be like more compact ways of solving this, but this was at least like my first attempt at this one. So I defined a class called inode, which if you're familiar with like actual file system implementations, the tree structure or like the tree node is called an inode in file systems. So the inode has a map from string to string of the files like we were talking about, and then of subdirectories, and the value in the subdirectories map is another inode. So that's where you get the nesting. And then I just have a couple basic like add methods for subdirectory and contents. If this was like a, like full, it would probably better to have like getters and setters for these as well, but I didn't want to make the code too long, so I just left those out. And then in my actual file system class, so I have my root inode, which again is like the file system node structure here. And my constructor doesn't really do anything. Like I just create a new inode. And then if you look at, so similar to the last question, if you look at these 3 or 4 actually, these 4 actual methods that we need to implement, there's like a very common pattern amongst all of them where you first traverse the structure with a given path, and then like once you get to that point, you like perform some operation. So to sort of reduce the code length, I have a navigate to path method, which takes care of my navigation. And since there's like slight differences in what you do in all of these, I created an enum called navigate options. So this has 3 options: ls, make dir, and add to file. So inside this navigate to path, yeah, this is kind of an edge case, but basically, so I start with the root inode, and I split the path by the path separator, which is the slash, just like most operating systems. So if you have like a path like A/B/C/D, this would give you an array of A, B, C, and D. So again, I just check like another sort of base case, like if that array length is 0, which can happen if they just pass the root directory, I just return the root inode. Otherwise, if it happens to be, if we're calling this from make dir, I take my path array, and then I actually, sorry, if we're not calling this from make dir, I leave out the last element of that array. So let me try to draw what I'm talking about here. So basically what this does for ls and for the other one, add to file. Right. So when I'm given the path, I actually don't go all the way to the path. I go like 1 from the last element, which is what this array copy does. So if you think of a path like A, because it'll just give you a path like A, B, C, D, let's say. I think that's one of the examples. So there's no like text, there's no like file type here. So you have to know that if you're given this path, this means that you navigate to this path, A, B, C, and then the last one, D, is the file name. So that's why I just copied the second up to like the second to the last element of the path. And again, so this is split into an array, so it'll be something like A, C, D. So for everything except make dir, I basically want to only navigate up to C in this case, and then that's what I return from navigate to path. So navigate to path will return the inode at C. And then let's take one of these examples. So like let's take ls, for example. With ls, what we do is once we navigate up to here, this can either be a file name or like a file or a directory because ls has to handle both. Yeah, I guess before I go to ls, maybe let's just finish this one. So I take all of these directories in the path array. And then if my subdirectory's hash map contains that current directory, I just advance my current node. So this is like the crawl variable in our last one that's doing the traversal. And if it doesn't exist, we just create it. I could probably leave this out. I just kind of added this for like conceptual reasons. But basically we added a subdirectory called with the key dir, and I take care of that add here in the inode class. And then after we create that subdirectory, we just advance the current node pointer again. Okay, so all of this method does, it seems kind of complicated because like I have to check like different things. I'm like using the same method for all 4 of these different functions, but more or less all it's doing is it's just navigating a path like this. And then in certain cases, it's only going up to the second to last element. All right, and then
it returns you the correct inode.
Yes,
okay.
Depending on how you call it with the options that you give.
Mm-hmm.
All right, and then again, ls, it looks like it's actually very simple. It looks like it's doing more than it actually is. So the directory like that we're interested in, we get from navigate path. We just call navigate path with the ls option. And then we have to extract the last element. So yeah, I can't really even remember why I needed this. I think there's like some edge case or something that I needed to call this. Let's see what this actually does. Extract final element on the path. So we split. Oh, okay, yeah. So what this is doing. Again, so your path will be like something like A, B, C, and D. So what extract final element does is it just returns like this last element, which is D.
Yeah.
And again, just made it a separate method because we will call it in all of these functions potentially, or like multiple ones. So then we just create our output list of strings for ls. And there's 2 possibilities here. Either what we had passed was either a file, like the last thing was either a file or it was a directory. So if we look back at the question description, okay, so if the path that you get in ls is a file, you return a list only containing that file's name. And that's sort of, I guess it's basically the idea is to just make it work sort of similar to how an actual ls command would work. And then if it's a directory, then you'd actually list everything in the directory. Okay, so ls can take either a file or a directory. So if it's a file, it's not really that interesting. You just take that last element which you extracted and add that to output, and then that gets returned. Otherwise, if it's a directory, let's see what we do. So we'll take. Yeah, you have to check for the root directory as kind of like an edge case. But the basic idea is that you just loop through the key set, which is like all of the directories at that level, and then you add them to your output. And since it wants it in lexicographical order, you just sort it before you return. Okay, does anyone have any questions so far? Those are like probably like the two most complex.
So the two question I have is, one of the directory does not exist. So I guess that's why you throw an exception up there, right?
Yeah, I could probably leave this out. I kind of just did this for my own like as like a sanity check kind of a thing. But if you look at the question description, it says that like one of the conditions is that it won't give you like, it'll only ask for things that make sense in the problem description.
Okay, so if it asks for the file, it guarantees the file is there.
Yeah, depending on which operation, like for
like
make
LS.
For LS, yes. See if I have that.
Yeah, it says in the notes you can assume all files and directories. If you go very down, yeah.
Okay, yeah, that's fine.
Yeah, you can assume all file or directory paths are absolute paths will begin.
Yeah.
Yes.
Some notes
And you
here.
can assume the all directory file names. Valid parameters. Second one, right? Yeah.
Right. Okay. So this is not like necessary for the actual solution. I just kind of put it there just to be exhaustive of like all the different possibilities. So that takes care of LS. That's really like kind of the most complicated one. Now, if you look at make-dir is basically as simple as it could possibly be. What make-dir does is it just traverses through the path that you pass, and then if you look here, let's see.
Line 56, no. Or line 58.
Yeah, so both make-dir and the add contents to files, like if at some point the path that you pass doesn't exist, you have to create it, which is actually here. So that's why I threw that exception over here, because in LS you don't want to create it. So I guess I just added this to like make sure that for LS we never actually create anything. But if you look here, this is the case where the directory key does not exist in the hash map, so we create them here and just advance to that directory. Right, so that's make-dir. Again, very simple. And then add contents to file, also very simple when you define, like when you have the navigate to path. So you call navigate to path, and then you just get that file name by extracting that final element of the path. And then you just say, for the directory at that path, just add file contents. And so this just adds this key value pair to the hash map in this directory. And then read is very similar. You extract the final element in the path, and then you just call get on the hash map rather than adding.
Okay. And where is the append? It does the same thing over here.
Append, so add to file, if the file exists already, yeah. So the append, I take care of that in this add file contents. So if the key exists already, then we just take the contents and append, or take the current contents and append the new content. And then we put that in the hash map. Yeah. So really, like the bulk of the heavy lifting is all done in the navigation method.
Yeah.
Right. So does anyone have any questions on this one?
This is the same as the try, right? But it does not
Yes.
look like the previous one. I mean, the previous one, you know, I look at it, it's like a try, but this one.
Yeah. 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 If you look at the actual operations and everything that's happening, it's very similar to the try. Yeah, I guess you have 2 hash maps instead of 1. There might be a way to combine that. And if you look at some of the discussions for this problem, that's a pretty common way that people solved it. Yeah, so there's try solutions. So you could look at those too. Yeah, a lot of people solved it with a try. Yeah. Any other questions?
So no question.
You can actually. Hello.
Yeah, go ahead.
No, I was just saying in C++ there's a concept called a union. So you can actually club both the files and directories into one. Only one gets used.
Yeah, that is right.
How would you do that? Both file and directory into
So
one.
you're saying like a data structure and use that, right? So whether it's a directory or a file.
Yeah, but it's kind of the same, right? It's like.
Yeah. Yeah.
I don't
like
have a question, but Hanif, in a 45 minutes interview, how can we come with such a big implementation? Like,
yeah, that's a good question.
Maybe because you actually went through the whole thing, you have some pointers for us to, take care of, or maybe do.
Yeah, I would say like probably like the best way I would describe that or answer that is all 4 of these are doing something very similar. They're traversing the path that you're given, and then based on like which operation it is, you just like carry out that operation. So I guess I would say like it would kind of depend on that. Like if you can define the navigate method, then the other ones become very easy. But I mean, it's a hard problem, I guess.
Yeah.
So it's,
But at least the way you make that navigate function generalized, made it more generic, so that helps. That will surely help.
Yeah. Any other last questions before we go to our last problem? Okay, so I guess we'll move on.
Yeah.
Right, so last one is a very commonly asked question to implement an LRU cache. So again, I'll just give everyone like a minute or 2 to read through the problem and think about it a little bit, and then we'll discuss. Yeah, so for the LRU cache, basically, as the problem says, you want to design an LRU cache. You have a couple of operations, which are get and put. And the idea is that you initialize the LRU cache with a certain size, and once you exceed that size, you have to evict the least recently used element. So any thoughts on how we should solve this one?
I think usually they go with a list of nodes or something like that, maybe linked list, and use another data structure to find the position of each and every key, or store that key in another data structure like a map, so it will be accessible in O of 1 time complexity.
Yes. So this is so this is kind of an interesting one, because like there's some problems that you can just solve immediately. Like if you just can think of the right data structure to use, that data structure will basically solve the problem. But then, like you were saying, so then there's some problems like this one that are a little bit more complicated, where it's, if you're trying to solve with this constraint where all of the operations happen in constant time, there's, at least as far as I know, I don't think there's like any single data structure that will solve this problem. And basically what you have to do is you have to combine multiple data structures to get the properties, like the desirable properties of both. So, and let's assume that we're, by the way, I see some people are like messaging in the chat. I'll read that at the end and try to reply to everyone if they're like asking me anything specifically, but I can't do both. So if people have questions, like if like either you can just ask me or somebody in the chat, somebody else in the chat can just like address the questions. That'd be helpful.
Yeah. I don't think there's any specific on this question.
Okay.
Yeah, there were the previous ones. Yeah. Okay.
Okay, sure.
There was no constraint of O of 1 time complexity here, right?
Yeah.
What would we use here? Would it be like just a linked list would be enough for us to?
Yeah, linked list would be enough, because it could maintain the ordering, because there's two things that you need for this problem, really. Like, so you have an LRU cache, and I think, let me just reshare. I think I only shared my browser window. Are you able to see the?
Yeah.
Okay, cool. Yeah, so let's say like you have this cache and you insert like 5, 6, 4, 3, 2, 1. And let's say that the size is 6. So at this point, the cache is at maximum capacity. And let's also say that these were inserted in reverse order. So the order that you insert things kind of matters here. Let's say that you inserted them as 1, 2, 3, 4, 6, and 5. Okay, so you can have a linked list like this, 5, 6, 4, 3, 2, 1. And basically the head of the list is the most recently used element. So if we wanted to insert 7 now, we would have to evict the least recently used element, which would be 1 in this case. It'll always be whatever is at the tail of the list. And then since we're inserting 7, 7 is the most recently used, so we insert it at the head. Okay, so that is the case of inserting. But for getting some arbitrary element, like let's say we want to get 4, and just think of these as keys, and assume that like these keys map to some value. Like these could actually be objects instead of ints, but just imagine that these are the keys of those objects within the list. So in order to get 4 or any arbitrary element, we have to traverse through the entire list until we find 4, and then we return that element.
So then that becomes the least recently used.
The most recently used, yeah. We would have to update this to, yeah, so it's the most recently used, and like the eviction policy is that we evict the least recently used, which would be 2 now. So a linked list is a good way of preserving the ordering that we want. We can always, like whenever we either get an element or insert it for the first time, we can move it to the front of the linked list. And then when we want to evict something, if we're inserting with max capacity, then we can just remove the last element.
I wonder if we use heap, would it, kind of work? Because if we take it out, we add it in, we add it, it always have we always have time, with a timestamp. So probably the oldest element will be probably the one on the top.
Yeah, that's an interesting idea. I haven't thought of using a heap for this problem. I'm not 100% sure if it would exactly work, or if you would have to like do some additional things. But if you're trying to shoot for the O of 1 complexity, a heap still wouldn't get you there. Like it would be log n for at least inserting an element. You can extract the least recently used in O of 1, but you wouldn't be able to do the other things with just a heap. But yeah, so with the linked list, this gives us a few properties. So we can, I'll say we can quickly find LRU element. And it also allows us to rearrange elements to the front of the list. So if you have some element can be moved to the head of the list, which is when it's most recently used. Okay, but the problem with just using the linked list is that you have O of n time to look up an element. So whenever you see, whenever you want to do lookups with an O of 1 time, especially like with this get and put interface, I guess the first thing that comes to mind is a hash map. So the good thing about a hash map here is you can quickly, and I guess when I say quickly, I mean like an O of 1, look up any key and return the value. But the problem with just a hash map, like a bare hash map, is that there's no inherent notion of ordering. So we can't maintain which element was the least recently used or most recently used with just using a hash map. So as you might have guessed by now, the I guess most common solution to this problem is basically combining both of these data structures, a hash map with a linked list. And if we have some, I guess some LRU cache element class, the hash map maps keys, which are ints, to objects of that class. And then the list also holds elements of this class, and they'll be the same elements. Like if you have 5, it's the same 5 in both data structures. Okay. Does anyone want to solve this one? I guess we're kind of low on time, so I can share my solution unless anyone like really wants to take this. Okay, so I guess I'll just share mine.
Yeah.
Right, so I used Java. And by the way, so when we do like the rearranging of these elements to maintain the ordering, like let's say we call get 6, for example, then 6 needs to move here to the head. So really the O of 1 rearranging only works if this is a doubly linked list, right? Because we have access only to that 6, and then to like do the rewiring of the linked list without traversing like the other part, we have to have a doubly linked list. So, and it turns out in Java, the Java implementation of the linked list class uses a doubly linked list. So it would seem at first that if you just use Java's implementation of linked list, which internally is a doubly linked list with a hash map, that you would be good. So let's take a look at that solution. So that's actually not this one. I believe it is this one. Let me see. If I show the code over here, is it too small or is it visible?
Yeah. Could you please increase the font size a bit?
Yeah. Let me see. I don't think this has a zoom function, unfortunately.
Okay. No problem. That's
yeah. So in that case, I'll just use the browser because at least I can zoom in the browser.
Okay.
So let me see. Get everything. Yeah. And let me try zooming. Let me shrink this. Yeah, I guess I should have zoomed in for the other question too. Sorry about that. So
fine. No.
Yeah, so we have a cache element which basically just has a key and a value. And again, in reality, we'd probably want getters and setters for this as well. And then as far as our LRU cache, we have the map, which maps integers as our keys to cache elements. And then we have, in this implementation, the Java linked list class, which will also hold the cache elements. And we also have a capacity, which we get passed as a parameter. So the constructor just basically makes these objects and sets our capacity.
Mm-hmm.
And then if we do it this way, the get and put are very simple. So if we call get, first we just check like the condition where the map does not contain the key, in which case we return -1. And that's just according to the problem statement. Otherwise, if we do have that key, we get that element by calling get on our hash map. And then we take our list, which I call order. We remove the element, and then it has this, the linked list has this add first method, which we can call to add it to the head of the list. And then we just return element.value. And then similarly for put, we check first if the map contains that key, in which case we just need to update the value of that key. So we get the element from our hash map. We set the value to the new value. And then to get the ordering correct again, we remove the element from wherever it is in the list, and then we add it to the head of the list. And then, so that's one case, like a complete case where we already have that key. But in the other case where if we don't have that key, first we have to check the size. So if we're already at maximum capacity, then we have to evict the last element, which is the least recently used element. So to get that, we call order.getLast, and then order.remove last, and then we also remove that key from our hash map. And then we just add the new element into both our linked list and our hash map. Right, so now my question to everyone is, what is the time complexity? Like, does this happen in O of 1 time? Like we would expect, since linked list is a doubly linked list?
Mm-hmm. So the get will happen O of 1 time, right?
Yeah.
So we're just actually accessing from map position of the key, right? And then we just remove it. Yeah.
So yeah, so there's a tricky thing here. Yes, so remove. In order to remove, you have to traverse to that element in this case. So it actually becomes O of n.
But are you not actually, when you say map dot get,
right?
So you are returning from, what is your map pointing to actually? Your value?
Yeah, it contains a cache element. So we have that element, like we have that element here, we have it in hand, and then we can call remove on that element. But we can't like actually internally go into the linked list and like rewire so that, like, let's say that like we have some elements and then we have like A, B, C. We have some more elements, and let's say that we're removing B, right? So for a doubly linked list, to remove an element, basically you have to say A.next becomes C, and C.previous equals A. Right, yeah, and then you would add B to the right position.
Yeah, because if you are given an address of a linked list to remove, so you can do that within a O of 1 operation, right?
Right, but if you look at the like Java remove for a linked list, it's not actually doing that. It's because these elements, like, they can't. This could be anything, right? So in this case, cache element is just this. So these elements themselves don't actually have the connections.
Right.
So there's no way that they can implement remove in an O of 1 way. That you have to traverse through the entire list and find the element. Which means
element, is element a pointer? I thought like everything in Java is like an object, which is a pointer, right?
It is, yeah.
Then if it is a pointer, it knows the address.
It knows the address, but the element, but look at my element class though. The element class doesn't have, because the only thing that we have is we have some instance of this cache element class, and these don't have the next and previous pointers.
But actually that element is supposed to be a value for the least, right? It's just a value. So internally it should actually have a node which will contain this value, correct?
Yeah, so it's...
And then it will maintain its next pointer. So that implementation is internal to that least.
Yeah, that's what I thought.
Yeah, because it should do that way.
Yeah, so I'm pretty sure that it's... I mean, that makes sense, I guess, but if you actually look it up, like we could say like...
Okay, yeah, so like that. Yeah, it might be.
Let's see. Yeah, so you could say like, why does Java's linked list take O of n time? Basically, like the point, it's O of n, I'm pretty sure, even though you would think that it could be O of 1. So you could see like remove are not O of 1, they require traversal, so it would be O of n.
Yeah, but in this case, we look at that API, remove object is O of 1, right?
Yeah.
No, that's what I just...
remove value is not O of 1, but remove object is O of 1.
Yeah, I could pull it up
So
again.
remove in general in the linked list is big O of n, I think.
Okay.
So both
Okay.
object and the key, yeah.
Okay.
So what that
At least
means...
we can assume here and say, okay, at least for the interview perspective, that should be fine.
Well, so what that means, and so you can actually see this in the runtime time, if you like, depending on how much you trust this. So there's like a factor of 10 difference here. So, and what you have to do basically in this case, like what I'm kind of trying to build up to, is that you have to actually build your own doubly linked list class in this case. So now when I redefine the cache element class, I have my previous and my next pointer, right? And then instead of using the internal like linked list class, I just basically make this like linked list on my own. I have the head and tail pointer. And then I also have to define the add and remove operations, or insert and remove this way. And then like these two, like the code stays the same, but you actually have to do your own. So I thought that was kind of interesting. Like even though Java's doubly linked list class, linked list class is internally a doubly linked list, you still don't get the performance that you would expect from a doubly linked list.
Makes sense.
For remove. Yeah.
So it might be true for others also, I think so. Not only for Java.
Yeah, I guess that, I'm not sure. Any last questions on this one?
I think it looks good, right? We implemented all, each and every feature of both the functions, the get and put. So
yeah.
in the put, we took care of, we just, if you want to update, or if you're exceeding the capacity, or if you're adding something new. So all the three cases are that, yeah. That's fine.
So one thing I was just trying to remember, like when I solved this problem, I did see some discussion where I am not recollecting it completely, but the question what I had written in my notes is, do we need a key and value to be part of our like the cache element what you have, or the node what we create?
Yeah. So
does the key needs to be part of it, because in the
right.
In the hash map we have a key and value, right? Like the map.
Yes. Yeah. So that's a good question. So if you look here at how I did remove, let's see. Yeah. So the thing is that if you look at this case where we're trying to evict the least recently used element, so this is basically the scenario where we delete something from our cache. So that LRU concept is stored in my list. So first I get it from the list, but then I have to remove that element from the map as well. So yeah, I guess, because I was thinking you'd have to remove by key, but I guess would this also work if I just removed the LRU element like that? And if I put this back, yeah. So I think you need the key.
So you're saying that during the eviction, we need this key to be maintained in the map.
Right, because we have to look up, because I think what just happened there is that, yes, because I think the removal is by key, unless there's like some other remove method that I'm not aware of for hash maps. I think removal is based on the key, so I think you need the key here.
Okay.
But is Sumit saying that why we need the input to be as a key and value?
Yeah, I mean,
makes sense. Yeah,
because the map has, I mean, the node what we are creating, like the cache element, right? Why do we need in line 4? Do we need the int key there?
You need the key to look up, right? You see if it's present or not.
but the value and key are the same, right? That is what
No, they are not the same.
Value and key are not the same. But he's correct in saying
if you look at the example, when you see cache port 1 and 1, so both of them are always same, right?
No. That's only this example, but that won't always be true. Like you can have any key mapped to any value. Yeah, it's actually kind of a stupid example because there's no reason they have to be.
If both are same, then we don't need to maintain both actually.
Exactly. Yeah. This is they could have used a better example here because it makes it kind of confusing. But
so that is the very reason, like for eviction, we need to maintain to have the key. That is the reason to.
Yeah, I mean, I'm trying to think if there's some way, like, yeah, as far as I can think, like this way, like you need the key in general, I think, to remove from a hash map. Not sure if there's any other way.
So for hash map, you need a key to do a remove. Yeah, that is true. Yeah. Or else you cannot remove it.
And the thing is that, like I said, so that LRU concept depends on first looking it up in the list. Mm-hmm. Right, so you look it up in the list first, and then once you have the element, you need to remove it from the map as well, and you remove like with the key.
Okay.
Yeah, I think we're basically at time. Well, I guess we have like 2 minutes left. Is it, like, any other questions or general questions about the meetup or anything?
Is that a similar way we use to solve the least frequently used?
No.
Yeah, so least frequently used is like a similar question to this one. I actually tried solving this. I thought of using a priority queue.
Almost same. Okay.
Well, this is not a working solution. This was like my attempt. But yeah, so it's not the same. It's a lot more complicated, basically, I guess is what I'll say.
Okay.
Especially like if you want to have the O of 1 time complexity. Okay. If you don't need to have that, then it's actually, you could do it with a heap, but yeah. Anything else?
Yep, that's good actually.
Okay, yeah. Bhavesh, I guess you could stop the recording and maybe see if anyone has any last questions for like the meetup or anything.